Hi, and welcome to Understanding Motors. So last episode, we talked about how you can use a modified H-bridge to control a brushless motor's commutation. This time, we're going to talk about how you can use it to modulate the current you send through your motor. So, let's get into it. All of the switching methods we're going to talk about this episode can be used with block commutation, meaning again that there will only be one phase connected to high and one phase grounded at a time. Because for this episode we're only going to be using two phases at a time, we're actually going to temporarily ignore the third leg of the H-bridge while we analyze the current dynamics of the motor. The topics we're talking about will hold true for a 3/2 bridge system. However, I find that it's easier to show and to understand if we're only looking at two of them. In episode 3, we talked about how you can send a pulse width modulated or PWM signal to the MOSFETs on the bridge to vary how much current is running through the motor. If we want a lot of current, we send a signal that closes the switch for the majority of the PWM period. The percentage of time that the FETs are written high during a single PWM period is referred to as the duty cycle. By moving the duty cycle between 0 and 100%, we can control the current flow between 0 amps and the supply voltage divided by the load's resistance. As we talked about in episode 3, from an electrical viewpoint, the motor acts not only as a resistor, but also as an inductor. This means that there's essentially a low-pass filter between the voltage and the current present in the motor. This is certainly true, but there's also other dynamics at play, and they vary with how you approach your PWM switching. In this video, we will be talking about three different methods, which I will refer to as hard switching, soft switching, and complementary switching. These techniques may be referred to by other names when discussed by others, but this is the naming convention I've been exposed to. Any PWM signal that is not at 0 or 100% duty cycle can be divided into two phases: the forced phase, where power is being driven into the motor, and the unforced phase, where it is not. The three switching methods we will be discussing all behave identically during the forced phase, but the discrepancies in how they handle the unforced phase drastically changes the electrical dynamics and the efficiency of the motor system. For each of the following three analyses, we will be commanding a current to flow from left to right through the load, and I'm going to introduce how each method differs before we talk about how the differences affect the system. Method 1. Hard switching. Like the other two methods we'll talk about, during the forced phase of hard switching, when commanding current from left to right, the high side left MOSFET is closed and the low side right MOSFET is closed. Thus, the left side of the motor is connected to high and the right side to ground. During the unforced phase of hard switching, both the high and low MOSFETs are opened. Due to the inductance of the motor, current will be forced to continue flowing from left to right in the motor. Thus, it will be pulled up from ground via the left low side MOSFET's diode and forced back up into the battery or power supply via the right high side MOSFET's diode. Method 2. Soft switching. During the forced phase of soft switching, just like in hard switching, the left high side and right low side MOSFETs will be closed. Unlike in hard switching, however, during soft switching in the unforced phase, only the left high side MOSFET will be opened. Thus, the current, which is forced to continue flowing due to the inductance of the motor, will flow up from ground through the left low side diode, through the motor, then back to ground via the right low side MOSFET. Method 3. Complementary switching. Again, like the others, the forced phase has, no surprise, a high left side and low right side MOSFET which are activated. Now, however, during the unforced phase, the high left side is opened and the low left side FET is closed. The current will flow up from ground through the FET on the left, through the motor, then back to ground via the FET on the right. So there are two main things that cause differences in dynamics between these switching methods. 1. The direct voltage applied to the load, and 2. The diode drops. We're going to start by looking at the direct voltage. In the case of hard switching, during the unforced phase, you're driving current up from ground to the supply. If you're using a battery, this means you're recharging the battery during this phase. Now I know what you're thinking. Recharging my battery is a good thing, right? Well, it's not quite that simple. We're going to talk more about regeneration in a later episode, but we'll just brush on it now. If you're pushing energy back into your battery, that energy had to come from somewhere, because energy is always conserved. For example, if we look at a car like a Prius or a Tesla using regenerative braking, the energy flowing back into the battery comes from reducing the car's kinetic energy as it slows to a stop. So, you're taking kinetic energy that you wanted to get rid of anyway and recapturing some portion of it. However, in the case of hard switching, the energy flowing back into your battery is energy your battery just spent trying to build the current up during the forced phase. Because this energy gets drained out of your system during each unforced phase, you will then have to run at a higher duty cycle than you otherwise would to maintain the same level of current, and regeneration isn't perfectly efficient. So you end up spending more energy during the extended force phases and getting back an amount of energy during the unforced phases which is less than the extra you spent during those forced phases. But the net increase in energy expenditure isn't the only issue here. In episode 3, we compared the current flowing through the inductance to the velocity of a heavy rock being rolled. Like with voltage and current, when you stop pushing on it, the rock will keep rolling for a little bit before it comes to a stop. However, if as soon as you stop pushing it forward, your friend starts pushing backwards on it just as hard as you were pushing it forward, it's going to come to a stop much sooner. In fact, unless you're pushing it forward more than 50% of the time, you won't be able to build up any speed. And if you think about it, this is essentially what is happening during hard switching. During the forced phase, you're pushing current with V volts. Then, during the unforced phase, the current is flowing up against V volts. So unless your PWM duty cycle is greater than 50%, you will not be able to maintain a current. This means that high-resolution current control is more difficult with hard switching. And, due in part to inefficiencies of regeneration, hard switching can be notably less efficient than its other two counterparts. These issues of hard switching are further exacerbated by our other source of difference, diode drops. I don't know about you, but when I first heard about diodes, I understood them to be components with infinite resistance in one direction and zero resistance in the other. But this isn't quite true. When current flows along the direction that a diode allows, it has a resistance that is inversely proportional to the current flowing through it. What this means is that, regardless of if you have 1 milliamp or 5 amps running through your diode, you will have a constant voltage drop across it. And this is what causes the other difference between these switching schemes. If you didn't notice before, during the unforced phase of soft switching, our current flows up one diode. Meanwhile, during that of hard switching, we flow up two diodes. In practice, the drops across these diodes are often over a volt each. For lower voltage systems, this can be huge and can cause current to decay much faster than it otherwise would. Essentially, while the current will continue to flow during the unforced phase of soft switching, it will have about a volt pushing back on it due to the diode drop. During hard switching, this will be over 2 volts, not to mention the fact that it'll be flowing against your supply voltage. This voltage pushing back on the current will cause it to decay more quickly, and this faster rate of decay makes high-resolution current tracking more difficult. Additionally, the resistive energy losses in the diodes during hard and soft switching means that your overall efficiency is lower. For all of these reasons, it is generally recommended that complementary switching be used during 6-block commutation. I know this video is a little bit longer than usual, but I want to take a brief detour here to talk about a misunderstanding I originally had about the amount of current running through your motor when you're using an H-bridge. A few years back, I was speccing batteries to run a device, and I started trying to calculate the size of batteries I needed based on the RMS current running through the motor. I figured multiplying this current by the battery voltage would give me the power out of the battery. Much to my confusion, when I checked this against the mechanical power estimations coming out of the motor, there was a pretty big discrepancy. So there's a couple of different ways to explain why the methods of calculation I was using there were incorrect. The quickest explanation of this is that, as I mentioned a few episodes ago, the voltage across the motor that is converted to mechanical energy is the back EMF, not the supply voltage. Because of this, it would be incorrect to multiply the motor current by the battery voltage and call that the power input. The other explanation, which personally helped me to understand this all more intuitively, is to look at the source of the current running through the motor. During the forced phase of the PWM cycle, the current running through the motor is coming directly out of the battery. During the unforced phase, however, the current is being pulled up from ground by the inductor. So if you're running at a 50% duty cycle, your motor is only drawing energy from your supply half of the time. And briefly, just to dispel any confusion you may or may not have about how this is energetically possible, I want to bring in a quick mechanical analogy. If you think about riding a grocery cart around a store, you spend some of your time pushing, then you hop on and coast. This is a little bit like what's happening in the motor. The mass of the cart, which is analogous to the inductance, allows it to keep flowing without you, or in the electrical case, the power supply, adding energy to the system. So saying that the power into the motor is the supply voltage times the RMS current would be like saying that the power you're putting into the cart is the cart's RMS velocity times the force that your leg pushes with. It's true if you're looking at a time period where you were pushing for the whole set. However, if you're looking at a time period that includes phases of both pushing and coasting, it's not correct to act as if your leg was exerting force F the entire time. That may have been obvious to all of you, but I know that when I was personally starting out, that was a real point of confusion, so I figured I would cover it. Anyway, now we understand the basics of 6-block commutation. However, 6-block commutation is not the most efficient or most effective commutation scheme. Next episode, we're going to dive into a helpful tool that we will use to develop a more ideal method of commutation.